All right, and we're back. We're on to the 12th unit review for our series. We're trying to cover all of the units in a kind of a bigger picture, just to give you some memories, remember some definitions, some big ideas. We don't go through everything. We just don't have the time for that. And we'll move on to the next one. And this video about redox and the video before about equilibrium are two of the videos that are most challenging for students. So let's try and maybe the second time around, things will make a little bit more sense for you. So redox, which is often the shortening of reduction and oxidation reactions, or oxidation and reduction reactions. This only happens when electrons are lost and gained. Okay, so electrons are either lost, well, actually, they're not either lost or gained. They are lost and gained. You can't have one without the other. Right? This would violate the law of conservation of charge. Right? You have to have the exact amount of electrons lost and gained in a redox reaction. Now, those two events, losing and gaining, are the foundation of everything that we are talking about. So losing an electron is called oxidation. And gaining an electron is called reduction. And so they have specific names for losing and gaining. And this is what everything in this unit is based off of. All right, oxidation and reduction, losing and gaining electrons. Now, when you look at a chemical reaction, there's only one way to really tell if redox has occurred. And that is through assigning and analyzing oxidation numbers. And so if oxidation numbers change in any reaction, you know, if some element goes from 0 and then it becomes a +1, or if something goes from a -2 and it turns into a -4, these indicate an oxidation number change, and therefore we know redox has occurred. We know oxidation and or reduction have occurred, depending on if we're looking at half reaction or full reaction. That's why I said or. So a couple of rules about atomic, one rule about the atomic numbers that students tend to forget is that when you have an atom that is bonded by itself, like sodium, or bonded to itself, like O2 oxygen, the assigned oxidation state is 0. All right, and that's a very important thing. Something by itself or bonded to itself can have the assigned oxidation number of 0. That will make things a lot easier. So we're just going to take all of that, right? Losing electrons, gaining electrons, and we're just going to jump it to the application section of this reaction, because a lot of the other review stuff comes into play when we talk about voltaic and electrolytic cells. So at the end of the unit, it always concludes with talking about voltaic and electrolytic cells. Basic overview: a voltaic cell is considered to be a battery. It is considered to be a battery. And this is because we get a spontaneous reaction, something that's happening completely on its own. The chemicals themselves are reacting and exchanging electrons. And in the process of them reacting by themselves with nothing helping out other than them just being in the presence of one another, is converting chemical energy spontaneously into electrical energy. Okay, this is a voltaic cell and it is spontaneous. It creates electricity just like a battery, and that electricity can be used to whatever you would use your battery for, a phone, a laptop, anything that uses a battery would use a voltaic cell of some sort. In a voltaic cell, you have two half cells that are connected by a salt bridge. The salt bridge has one purpose, and it allows for the flow of ions. When you start taking away electrons and adding electrons, you start creating negative ions and positive ions. The salt bridge's purpose is to balance the change that is occurring in each end of the half cell. So as we get into, at the end, like I said, I'm going to have a little example that we'll work through, but we have to remember that we can figure out in a voltaic cell what's being oxidized and what's being reduced, because we can look at table J, something that we are given on the Regents. And the higher up an element is on table J, the more oxidized it's going to be. Okay, so you would find gold at the very bottom of table J. You would find sodium way up top. If we were analyzing these two elements, trying to figure out what was being oxidized and what was being reduced, the higher up element of sodium is going to be the one oxidized. Now, the other cell is called an electrolytic cell, but it doesn't matter if we're talking electrolytic or voltaic, because what we have to be able to do is that understand that in both of these cells, the site of oxidation, wherever oxidation is occurring, is going to be called the anode. Okay, anox. The anode is the site of oxidation, while reduction is always going to occur at the cathode. And the way the electrons flow, and this is where I need you to, use your brain a little bit and think about it. If the anode is the site of oxidation, that's the place where electrons are being lost. If the cathode is the site of reduction, then that is where the electrons are being gained. So then logic tells me that the electrons always have to be flowing from the anode, the place of losing electrons, to the cathode. And in the example I gave before with sodium and gold, if sodium is the thing being oxidized, then sodium is the anode. Gold is being reduced, then gold is the cathode. So in that example, the electrons would be flowing from the sodium to the gold. Now, we have to use all of this information to piece that information together. And the last thing before we move on to the little example is, let's just talk about an electrolytic cell and how it's different. An electrolytic cell is opposite of a voltaic cell in many ways. The one way it's not opposite is the anode is oxidation and the cathode is reduction. But in order for you to have an electrolytic cell, you have to have an outside energy source. Typically, I mean a battery. I could also mean a plug. There needs to be some form of energy input into an electrolytic cell in order for it to operate. And the reason you need the electricity is because we are forcing a non-spontaneous reduction and oxidation reaction. Right? We're doing something like in my sodium and gold reaction that I was talking about. We can reverse that. We can make the gold be the anode where oxidation occurs and sodium be the cathode where reduction occurs. even though it violates table J, we can do that if we hook it up to a battery, right? Because we are going to use that electrical energy, and we're going to take that electrical energy and we're going to use it to reverse and bring back the chemical energy in the original reaction. And that's non-spontaneous, right? Gold does not want to oxidize to sodium. Gold wants to take the electrons. It does not want to lose them. Okay, so that's kind of just like definitions and overviews of redox. Now let's look at an example and we'll kind of try and break it down. So in this picture, it just shows what we were talking about. All right, and you know what? Since we've been talking about it a lot, let's use it right here. This side is a sodium electrode. This side is a gold electrode. Okay, and what is happening in the course of this situation is I identify Na as the anode, not based on the picture, although that would obviously help, but you won't be given all of this information. This is what your brain has to fill in. I can identify it as the anode because it's higher up on table J. Right? It will be the thing oxidized. And gold will be the cathode for the opposite reason. Once I can do that on these cells, I know what's happening. I'm losing electrons here. I'm gaining the electrons here. And the electrons flow, as we said before, from the sodium into the gold. Now, once you can identify that, we can figure out what the heck is happening. So this is a little review on half reactions, okay? Slide this over so a little lower. The sodium anode is being oxidized. So I know that I'm going to be creating sodium ions because I know that I'm losing an electron. This is a half reaction that shows oxidation. Right? I've lost the electron, oxidation, the oxidation number increased, oxidation, sodium became an ion, oxidation. All of those reasons explain why this is oxidation. And at this cell, these sodium atoms that were a part of the electrode move into the solution. They are now dissolved ions. All right, and what ends up happening, because I'm adding all of these positives into this solution, the salt bridge, as discussed before, takes some unknown negative ion through diffusion and balances out the change in charge that we are seeing. All the while, the electrons are moving through here, creating electricity that we can then use. And as that electricity and electric current continues, I use a different color other than green. How about orange? Right. They come down here and the silver ions are reduced. Silver plus becomes silver metal. And I know this is reduction because it is the cathode. And I know that in reduction, that electrons are gained. And so my electron has to be written on the left side of this equation to show that the electron has been gained. This is how oxidation and reduction occur in a voltaic cell. Spontaneous, it happens on its own, nothing is happening. to make this happen, one tiny final detail, right? If these atoms are becoming ions, the mass of this electrode is going down. Eventually, the mass of the anode is gone completely, and the battery stops working. That's when a battery dies. Meanwhile, the mass of this is increasing because I am adding more electrons to make more ions. Now, in a electrolytic cell, like, I hope that you could identify immediately a voltage source, not a voltmeter, a voltage source, a source of electrical energy. This right here, indicator. I know immediately this is a electrolytic cell. Input of energy. Electrical energy will be converted into chemical energy. And this is a perfect example of an electrolytic cell, of plating, electroplating, where we're taking a silver anode, we're not melting it, we're dissolving it, right? Creating these ions that swim around in the solution. And eventually those ions, once the electrons, the negative electrons, move from one side to the other, the negative electrons attract the positive ions and they reduce. So in this example, silver is both oxidized and reduced. It loses its electron through the wire, swims around the solution, and finds its electron when it gets close to the other side. The one thing, though, that you should take note in is how are you supposed to know what's the anode and the cathode? Right? Because we can't use table J to look at silver versus silver. They're the same thing. So pluses and minuses let us know that in an electrolytic cell, the positive end of the battery will be hooked up to the anode, meaning the negative end of the battery will be hooked up to the cathode. And so we would be able to tell that the silver bar is being oxidized and the spoon is where reduction is taking place. So that's a really, on the surface, a little bit more in depth than on the surface, but coverage of oxidation and reduction. There's a lot to this unit. And just like in the last unit, you should definitely go and practice this and talk to me or your own teacher about what it is that you might be struggling with. And you can get some one-on-one help for those particular topics. So if you enjoyed the video, whether it was a little bit or a lot of it, please do me a favor, hit the like button, subscribe to the channel. I greatly appreciate it. I hope that this is helping you at least prepare on some of your deficiencies that you might have, or at least it's giving you a good broad overview of what to expect come your finals time. So I'd like to thank you very much, and I will catch you in the next video. There are only a few left, and don't stop now.